Okay, welcome back. This is Chapter 3. Chapter 3 is all about hardware kinds of things. And if you read the book, which I hope that you're actually doing, they go in an awful lot of details, and I'm going to skip over some of the details just because it's not all that relevant for most people. At the beginning, page 104, they go over the chapter objectives. That's actually pretty decent stuff. So let's just look at the objectives. So the idea is, computer hardware must be carefully selected. Again, now look at this from the context of you're in an office environment and you're trying to help the automation folks make a decision to buy something, for example. So you need to know enough so that the salesman just can't come in there and say, "Wow, you need to buy this." So yeah, select the environment for the stuff. Hardware industry is rapidly changing, and so you need to describe, different kinds of things. So learning objectives. Describe the role of central processing unit and primary storage. Basically terms. State the advantage of multiprocessing, parallel, and grid computing. Describe access methods, capacities, and portabilities. Identify and discuss the speed, functionality, and importance of various input and output devices. Identify the characteristics and discuss the uses of various class of single-user and multi-user systems. Describe Moore's Law. And give an example of recent innovations in computer stuff. Identify some of the challenges and trade-offs that must be considered when you're doing a data center. Define the term green computing and identify several benefits to green computing. Okay, so that's essentially the stuff. I always like the gold section, page 106, where they actually talk about why am I learning this? What is the purpose? So why learn about hardware? And I already kind of sort of told you the story. Basically, the answer is, hardware is a very rapidly changing thing. I mean, there's new processors are being come out, every 6 months, and there's new stuff going on, new breakthroughs, and, your company is probably going to have to invest in new hardware sooner or later. And so you need to know enough about it to be able to not be confused by a slick salesman. That's essentially what we're after here. So yes, investments in hardware can improve the productivity, increase revenue. Anyway, bottom line is managers, no matter what their career field and educational background, are expected to help define the business needs. The real issue here is you basically have two worlds. You have the business world and you have the IT world, and you have to be able to talk right in the middle. That's what this course is all about, is to give these people over here enough about the language over here, and these people over here know enough about the language over here, so you can talk. If you can't talk, well, then you're going to end up in a mess. So that's essentially why you want to learn this. Okay. When they start off this chapter, they start off talking about, the power of technology. Dun, dun, dun. They start talking about the main components, and they have this little diagram of a computer, and you're supposed to drag and drop all this stuff. I'm not going to do that. But the idea is that the central processing unit. Now, here is, if this was a computer science course, a CS course, I would be really deep on, what the heck is the central processing unit. The problem now is the word CPU, central processing unit, is misused probably more often than it is used correctly. So, for example, you call up the help desk and they say, well, turn off the CPU. Are they talking about a chip the size of a postage stamp? Is that what they're talking about? Or are they talking about the box that you got sitting on your desk? See, that's the problem. Most people say it wrong. So, the box, the CPU, the tower, all those kind of things. That most people just call that the CPU box or some goofy thing like that. It's not exactly correct because in this case, it's a tiny, tiny little chip, but that's okay. And the other problem is, of course, that you have the all-in-one computers, like a lot of the Apple computers and some of the newer ones, where the actual CPU itself is inside on the back side of the monitor, so you don't really have a box. All you have is a thing with keyboard and a mouse. I got my mom one of those, has a wireless keyboard, wireless mouse, and then this one, 17-inch monitor, and that's it. That's all she has. And so if she was to say, "Where's my CPU?" I'd say, "Well, you don't really have one," which is technically not correct. Okay. All right. I'm not going to go into all the details about, the arithmetic logic unit and controls and registers and blah, 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 buses and stuff like that. That's a little too deep for the kind of things that we're supposed to be doing here. Okay. I am going to talk about primary storage. Primary storage is a strange term. There's primary storage and secondary storage. So primary storage is basically the amount of memory you have in the machine, the random access memory, RAM. And so primary storage is like a holding area for doing work. Okay, it's like my workbench. I put all of my supplies on my workbench and then I work on something. But as soon as you turn the machine off, boom, workbench gets cleared out. When I turn my computer off, there's nothing in memory whatsoever. So whatever was in there is gone. So it would be considered transient. So transient use of storage goes away when it gets turned off. So primary storage is the RAM. Okay, that's basically the takeaway here, as much as it says. So this is a little too deep in the weeds. I'm talking about the FET's instructions and all this stuff and how the inner working of the CPU works. No, I'm not doing that. I will tell you just a little bit about how you determine processing power. So let's say, for example, you have two computers and you want to know which one is going to be faster than the other. Like you're trying to decide between Model A and Model B. And so which one of the ones you want to buy. So there are ways you can determine CPU performance. And one of them is what's called machine cycle time, or clock speed. So clock speed is typically in gigahertz now. So I have a 3.5 gigahertz processor in my laptop. Things of that nature. So it's a numeric number that is designed so that if you had the exact same brand and model CPU, and one of them was a 3.0 and the other one was a 3.5, well then obviously the faster one is going to be faster. Okay, now that comparison only works when they're using the exact same models. So I know it's a little confusing, but just bear with me. So let's say, for example, I have an Intel Core i3 processor at 3 gigahertz. And then I have an Intel Core i7 processor at 3 gigahertz. They're both running at the same clock speed. So are they going to be equally fast? Well, no. There's more things to it than just clock speed. So the i7 processor is going to have more stuff. I'm not going to get into too much detail, but it's going to be faster. So clock speed alone is not a good measure. It is a measure, but not the only measure. Okay. In the old days, clock speed was fixed. You bought a processor and it ran at 1.7 gigahertz, and that's it. That's all it did. Nowadays, practically every processor, even on tablets and stuff, have a base speed. And then if it gets a little bit of load, it can speed up or slow down to ramp up to the need and then drop back down. And the reason they do that is you're holding onto a tablet, and if you had it at the highest speed at all times, the little sucker would get hot and it'd drain through the batteries in no time at all. So they want to be able to have it, spin down, so to speak, and use very little clock speed and then spin up when it needs to. So this variable range of clock speeds is how almost all modern processors work. Okay. There's a section here that talks about Moore's Law. And the idea is that what happened is, I'm not going to go for the goofy demo there, but what they basically said, this is a researcher and used to work at IBM, and he basically said that the rate at which the number of transistors that appear on a processor doubles about 18 months. So every 18 months it's going to get essentially more, which doesn't necessarily mean faster, but basically what it's saying is that every 18 months your processors are going to get more and more and more and more and more complex. So that's Moore's Law. You can click on the little doodad here and bring up a Wikipedia article, or you can watch the little goofy video. But anyway, bottom line is Moore's Law basically says that if you just wait a few months, there's going to be a new one coming out, and it'll be faster than the one you had. Okay. All right. The next thing we're going to talk about is capacity measurements. So now that I've kind of got the idea, the CPU has lots of different measures, one of which is the clock speed. When it comes to storage capacity, there's typically two different measures you'd want to know. One is its memory has a particular size, a capacity. It also has a speed rating. So let's talk about capacity first. So you'd hope that computer storage units, a byte, a kilobyte, blah, 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 blah. You'd hope that all that made sense. And I've already kind of mentioned in a previous video that that's not exactly the way it works. That when I'm buying RAM, if I went to the store and bought a stick of RAM and I said I want a 1 gigabyte RAM, I am not getting 1,000 to the third power. I'm getting 1,024 times 1,024 times 1,024. However, if I went to that very same store and said I wanted a 1 terabyte hard drive, well then it is. So RAM uses the 1,024 base number. Hard drives use the 1,000 base number. And so you just basically have to translate in your brain when they mean kilobyte, megabyte, terabyte, what the heck they're talking about. Because sometimes it's fairly obvious and sometimes it's not. So I do not think that this is a very good chart because they probably should have shown the other one to be able to make sense of it all. Okay. A bit. A bit is just the tiniest little thing. It's just a yes or a no, okay? And I'm not going to try to visualize that. But it takes 8 of these things to make a byte. So a byte is made up of 8 bits. Bits is the lowest. You can't go any further than that. So 8 bits to a byte, 1,024 or perhaps 1,000, depending on what you're talking about. Bytes into a kilobyte, etc., etc., etc. All right. Remember when I talked about how to make sure this is not ambiguous, you'd use the I, KIB, GIB for gigabyte, anyway, the new technique for making sure that everyone is on the same sheet of music, because this could get confusing. Okay, they talk about memory types. So random access memory is usually the stick of memory that you buy at the store and you crack open your machine and you plug this thing in and button it back up, and now your machine has more RAM. I'm not going to go into the types because there are lots of different subtypes, but that's kind of boring. They talk about cache memory. Cache memory is one of those things it used to be separate, but now the cache memory is inside the CPU chip. So when I buy a chip from Intel or AMD, I buy the chip. Inside that is my CPU and my cache. Actually, there's several levels of cache. But cache is designed to be very, very high speed because the CPU can run it blazingly fast, but the memory is kind of slow. And so what they do is they put something between the very fast and the slow. They put something in the middle to kind of help speed it up. That's what the cache is all about. Now, if you had all the memory in the world, money in the world, you could do your entire machine in cache, and it would cost you, several $1 million to do so. But you could do it. You could get away with it. But that's just not practical. So all CPUs now have some sort of built-in cache. Okay. So essentially between the memory, which is kind of slow, and the CPU, which is kind of fast, it just kind of helps determine, helps speed things up. Okay, this is a good place to stop for the 15-minute mark. We'll pick this thing up again in just a few.